So, welcome to the course today. We are going to continue today with graph-based SLAM and look into one instance of graph-based SLAM which we haven't talked about before. So far we basically used pose graphs. It means the graph that we were considering only contains robots' poses. And from a formulation point of view, if we are working in the context of landmarks, so distinct places in the environment that the robot can perceive, then it would be actually more natural to also add those landmarks to our graph and perform the optimization including those landmarks. So mathematically what we have done so far, we actually marginalized out features in the sense that we created kind of local maps, and we had this concept of the virtual measurement which relates to poses through the environment or through the measurements that were taken at those locations. And if you formulate this as a full graph and then kind of eliminate features in the environment, you can actually see that or frame that the pose graph is a variant of the original graph where the features have been marginalized out. And so what I would like to look into today is if we don't work based on grids, so if we really observe landmarks in the environment. These landmarks can be, let's say, the example we had before, the trunks of the trees, if we have seen that in the Victoria Park, or can be visual features that you observe with the camera. This can be whatever corners that you may extract from your sensor observations in the environment, where you can estimate, for example, where those corners are. These are all possible features, and the question is now, how can we actually integrate that into this graph-based SLAM framework? And we will do that by adding additional nodes to our graph structure, or to the graph structure that we have seen so far. And simply, we won't have the effect that every node is a single pose where the robot has been in the past, but we will have additional nodes, for example, for features in the environment. So if you looked at what we have done so far, we said we will use a graph, and this graph consists of nodes and edges. The nodes of the graph corresponds to the position of the robot during the mapping phase. So this is how we defined it before. So we had only nodes which can be the poses of the robot at different points in time. And we had edges, and the edges connect always two poses of the robot. And this was done either through odometry or through this concept which we called kind of virtual measurement. And what changes now is that we will have different types of nodes, and we will probably also get somehow different kind of edges that we need to consider in our framework. But the rest stays kind of similar. So we have that graph, and we try to find the configuration of the graph that minimizes the error that is introduced by those constraints. Of course, if we add new edges or new types of edges, we will also have a different error function that we are going to use. So this error function strongly depends on the sensor that we are using, what kind of error functions I'm using. So far in my framework, we had these vertices, or the nodes in the graph, which were just robot poses, so x, y, and its heading theta. That was what we had so far. And we had these virtual observations or transformations, which were in the end boiled down to transformations or rigid body transformations between nodes, or between poses the robot has been. And today the question is how to deal with landmarks. And we will do that by adding new vertices and adding new edges to our graph that represent features, and then we can also, for example, optimize. Through the optimization, we also change the location of the features in the environment. So we see this as one of those illustrations of the vehicle which drives here over a surface, and we have those, let's say, landmarks, which can be seen as these guys over here. And then the graph should not only contain the poses of the robot at the different points in time, but also the position of those landmarks, which are again assumed to be static. I had so far the example with the trees, with the landmarks. So this is an illustration from the Victoria Park dataset that you have seen already. We used that, for example, or seen that, not used that, in FastSLAM, which was the simultaneous localization and mapping problem addressed with a particle filter. And we had the robot driving around, and we have here estimates of features, and those features were generated from the trunks of the trees. And so you see a couple of places where there is no tree, like this one over here. This can have multiple reasons. One of the reasons is maybe there was something standing as the point in time when the satellite image was taken doesn't correspond to the time when the robot was driving, or the car here, in this case, was driving through the environment. On the other hand, a couple of them can be wrong observations. So for example, if you go here, these were quite likely to be cars, which were simply identified as possible trees. But this was just because a quite simple detector was used. But there will be observations which are, or landmarks, or quite likely, which do not correspond to the reality. But what we would like to have in the end is a graph which does not consist only of those blue lines, which is the trajectory, which would have been the graph that we have before, plus interconnections, of course, but also links to all those landmarks. So the graph will actually grow. There will be a quite large number of new nodes coming into the game. So if we kind of want to draw this graph, this is what the graph now would look like. So again, we have those triangles, which are the positions of the robot at the different points in time. We maintain that. But we have additionally those stars, which are here, landmarks, or future observations that the robot has seen through its sensors. So these edges here are my odometry edges. And the robot here says, OK, from this point, I see this feature and this feature. And here says, I see this feature. When coming down, he sees this feature. And through seeing the same features from different location, I can actually relate those two poses with each other. So through seeing the same feature, we can know something about the relative pose, or get some information about the relative pose of those two robot poses. So if I marginalize out features, in this case, this will generate a link between these two positions. So marginalize out the feature, kind of they see the same part of the environment, if you want to, and then you generate a direct link, and this corresponds to marginalizing out the feature locations from a mathematical point of view. That's what we have done so far, and today we'd like to look into what happens, or what typically happens, if I integrate those landmarks as individual nodes into my graph structure. So kind of clear from the idea, or are there any questions about what we have done so far about the pose graph itself? So what are problems that you could envision that could appear in this context? Any idea what maybe not so straightforward? Yeah?
Yeah, the assignment of the landmarks, so that we know it's the landmark that we've seen before, or it's not, so we don't know.
Yeah, so the data association between landmarks is definitely a problem in here. On the other hand, we actually had the same problem before, if we are honest, because before we needed to make the decision, is this the same part of the environment that the robots observe, and through the sensor observation we kind of related the poses, which is actually solving, I don't want to say exactly the same problem, but more or less the same problem. Once you maybe do that on the basis of full scans, and here you may do this on the basis of individual features, but the underlying algorithm which makes the decision these two places are the same place are very similar. So this is not necessarily something that you would say this is very specific to this problem. You may need to address this based on your feature representation, and the question is how to kind of get good feature descriptors which describe these features. This is definitely a point, but the data association itself, it's slightly different, but it's not something which is structurally different in this kind of problem. Or what are typical sensors you can imagine to observe those features? For example. So what do you see if you see the trunk of the tree with a laser rangefinder?
Distance to it.
You know the distance to it, and you know the heading to it. Okay, so we know where the trunk is. So if you see the trunk from one position and we see the trunk from a second position, what do we know?
We know its position relative to two nodes in the graph, or to two robot poses.
So if we observe the landmark, so I see the landmark now with the range and bearing observation, and I'm at some further point in time where I don't know where the robot is, I see the landmark again. Can I relate them? Okay, let's simplify the problem a little bit. If we have just a camera, we just see one feature in our camera image from one position, and I see the feature, that's exactly the same feature in a different image. So only know the direction in which this feature are. Let's say we are kind of in the 2D, we're still in the 2D world. What about that? Do we perfectly know where the robot is? Exactly. So depending on what we observe, what kind of features we have, and what the properties are that our sensor has, we may not be able, for example, to relate those two poses directly with each other, saying, hey, this pose is whatever, 1 meter away from this pose and in this certain orientation. Because we may only observe, for example, the orientation or the heading, or it's called the bearing to the landmark. So it's what's called bearing only SLAM. If I can only see bearings, so the heading towards a landmark, and if I see the landmarks from two positions, it's simply not sufficient to reconstruct where the robot was, or what the relative transformation between the positions of the robot where those observations have been taken. So I may not get an edge between them which is sufficient to, in the sense of the degree of freedom that the system has and what my measurement provides me. That is something which can lead to problems and which also needs to be handled in a certain way, or at least differently than it was before. It's kind of one of the main differences that we have in this type of problems. Okay, so the graph that we have now, this kind of graph over here, we have now two types of nodes. One are the robot poses. These are, again, our blue triangles over here. And we have the features, so our landmark locations, which are those stars over here. So we have two types of those nodes. The edges that we typically have are again one type of edge for the observation. That's a different observation than this virtual observation that we had before. Typically the information that you obtain from one of those feature observations is less than you would get it for a full view of the environment. So you need to accumulate multiple features, see multiple features at the same point in time. Then you can again reconstruct the relative positions of the robot. But that kind of depends a little bit, as I said, on the exact observations that you have. And if, for example, if you can only identify the relative XY pose of a landmark, or if this landmark has a special orientation, that you can also identify the orientation. So if the trunk of the tree and they turn the trunk of the tree, there's no distinct heading, which also makes it more difficult to actually reconstruct the poses. And of course, we have our odometry measurements. What we don't have anymore are these direct pose-to-pose constraints resulting from observations. So our virtual observations, that's something which we don't have in here anymore, because we only operate based on our features. But again, the minimization task is the same one. We want to find a configuration of the nodes. The difference is now that the nodes include the robot's pose as well as the position of the features or landmarks. I want to find the configuration of the nodes which minimizes the error introduced by all those constraints. So the underlying minimization problem again seems very similar, except that we have different types of edges and different types of nodes in our graph, or at least partially different ones. Okay, let's look back. Let's say start with a more easy example. We have a landmark or a sensor which tells us the relative XY location of a landmark. So if I'm looking here, I'll look somewhere and I can see this feature. I say, okay, this is the delta X, whatever, 3 meters, delta Y, 1 meter. Something we can extract. So every of those observations, if this is a vehicle and this is a vehicle feature observation, says, okay, this feature is, let's say, whatever, 5 meters to the right and 1 meter to the front, whereas this is 5 meters to the front and in the zero to the side. So these, assume for the moment we have these kind of observations. What would an error function look like? So the positions are now here just 2D points in the space. So we just know the XY location of those features. So we have robot's poses, which are 3-dimensional, X, Y, and the heading, theta. But for the landmark pose, we only have 2 dimensions, X and Y. But we need to take into account here in our setting. So how would an error function actually look like? One observation, so how we can actually model compute the expected observation, and the expected observation then leads us to the error function.
difference between the real measurements?
Of course, the expected observation is something we had as well in the EKF, and we had it exactly in the same way for the landmark-based SLAM as well. So computing the expected observation is something you need in these frameworks, so least squares approach as well as in the EKF, where you need to compute what is the expected observation given my current state, which is here, what is the current configuration of my graph, and I compare or I evaluate it by taking into account the expected observation and comparing it to the real observation. And by having the mismatch between the real observation and the expected observation, I come up with an error function. That's very, very similar. So what do I have? I have the pose of the robot and I have the pose of the landmark given my current graph configuration. So the only thing I need to do is what is the delta x and the delta y from the position, from the relative position between both of them, taking into account also as well as the orientation. So that's what I kind of need to do. And if I write this, I actually write that quite easily. So the expected observation of xi, xj, xi is here, the robot xj is the landmark. I can express this as the rotation matrix, which results from the orientation of the robot. And here I have the position of the landmark minus the translation of the robot, so where the robot is in the space. What this gives me is a two-dimensional vector of x and y, or relative x and y, where I expect the landmark to be relative to the robot. So that's the way the robot should observe the landmark. If the configuration of the graph of the robot and the pose are exactly the same, I expect to measure that. It's my expected observation again. Okay, so I have the current configuration of the graph, and what would I expect to measure there? It's kind of how the robot relative to the landmark in terms of delta x, delta y, which takes into account where the robot in the space in the global reference frame, where's the landmark in the global reference frame, and what's the orientation of the robot. So this is the position of the landmark in the global reference frame. This is the part of the xy part of the robot's pose. So and this is the orientation. So this just says what's the delta x, delta y in the global reference frame, and then rotated into the orientation of the robot. So if the robot is rotated, 90 degrees to the left, you need to rotate that from looking forward to looking sidewards, or the other way around. So this is the expected observation. We perform this operation, given a graph configuration, we compute what the robot is expected to measure. Okay, how do we bring that into relation with what the error function will be? So what is the error function which would result from that? Mm-hmm.
It's always the expected value minus the real value.
So it is the expected value minus the value that I actually measured of ij. Right? So it's exactly correct. This is the pose of the robot. This is my landmark. The error is the difference between both of them. So if I measure delta x, delta y, this will be a two-dimensional vector of x and y, and this as well. And if I subtract, then I know by how much in x direction, how much in y direction the observation doesn't agree with the current configuration of the graph. So if I just write this down, this is straightforward. It's just Ri transposed xj minus ti minus that ij. And this is something which I directly compute from xi. Here we have xj. This also comes from xi. And this is the expected observation that I know as well. So all the terms are given. So this is the expression that I'm trying to minimize. So this is my error function in this case. So it's the expected observation minus the observation that are obtained, and this is directly formulated like this. Okay. What happens now if my landmark is not, or what I observe about my landmark is not a delta x, delta y, but it's just a heading. So we still have a feature still given by an xy position in the space, but I can only observe the heading, the orientation of the platform, or kind of the angular part of the state space in this case. How would I do that? What is, again, the expected observation? So still the thing should have still an x and y. Still have an x and y position for our landmark, but we only observe a heading, so the bearing to that landmark. So again, we have kind of my expected observation, that ij of xi, xj. So how do I compute the expected observation for this case? So given two configurations, where the robot, where the landmark according to the graph, how do I expect what I should measure in terms of orientation? So you can see this, if you plot that, x, y, this is the position of the robot, this is the position of the landmark. Maybe the robot looks in this direction. How do I compute this guy? One part we need for that is the offset delta x, delta y. It's something which we may exploit if we want to do that computation.
You use sine and cosine in some way, but you don't know the distance to the landmark. You only get the line in some way. That's the point.
So a tan delta y delta x. This gives me this guy over here, alpha. That's my alpha. And then this is the full heading of the robot at the moment. I'm interested in this guy, so I need to subtract the orientation from that, minus the orientation of the robot. Robot's heading. This delta x and delta y is just something which is directly computed from the x and y location. So this is, if you go to this plot, so this is delta x and delta y. This is the orientation of the robot down here, because this is the x-axis. So whatever. This is orientation I, that's the way I called it. This theta is the theta ij, so the what it observed. And this is the alpha, which results from the relative offset in delta x, delta y. So this is alpha, and if I subtract alpha minus the orientation, I get exactly this orientation over here. So which is negative in this example, which is correct because it's turned to the right side.
And this is the heading.
This is the expected observation. So given the robot is here, looking in this direction, given the landmark is here, I'm expecting to observe this, whatever here, in the plot called theta ij. But the expected observation. Okay, is that kind of clear? Really clear or only kind of clear? Good. Okay, so we have exactly what we did on the blackboard. So this is exactly this expression here means delta y. So this kind of the positional difference in x and y of the landmark and the robot's pose, and taking the y component, x component. So this is delta y, this is delta x, atan, and so atan 2 if you implement that to make sure you have all four parts of the reference frame correctly mapped. So if you implement that in your favorite programming language, atan 2 is a function to use for that. And we subtract from that the robot's orientation or the current orientation of the robot. So again, if we go from the expected observation to the error function, what do we need to do?
Yeah. Where do x and y come from?
this thing?
Yeah, the landmark position.
Yeah. So what this is the expected observation. Given the current configuration of the graph, we want to compute what do we expect to measure. And as the landmark is part of the graph, there's a two-dimensional state vector, x and y. This is, given that's what the graph looks like at the moment, I'm expecting to measure that. This is the expected observation. It's not the real observation, it's the expected observation. The real observation is just the thing that the sensor provides. Where did I stop? Exactly. So now I have my expected observation. How do I compute the error function? Same way as before. That's a pretty good segment. And an epsilon more in detail.
Expected observation minus
Real observation. So exactly, we have exactly this term over here minus the bearing that we actually observe. If this is 0, that means the orientation fits perfectly. So I'm measuring what I'm expected to measure. If I'm off by a large degree, that means there's a big mismatch. And then I'm trying to minimize the difference in the orientations. That's what's for bearing only slam. So depending on what the properties of that's actually how it looks like then. This is exactly the properties that simply results from the landmarks and your sensor. So if you can only determine the heading, you only have a one-dimensional error function. If you obtain, let's say, 2 dimensions, delta x, delta y, or whatever distance and orientation, you obtain 2 dimensions. Maybe you can estimate also the heading of the landmark. So if the landmark has an own heading, for example, this can be the case if you have special markers or tags that you put somewhere. You actually get also an orientation, how the things are oriented with respect to the sensor. Then you may get a 3-dimensional error function. Depending on the dimensionality that you obtain and the degrees of freedom that are involved in the system, you can actually directly reconstruct the 2 recording poses, or you cannot. At least no unique solution. So you gain some information, or you restrict the solution space, but maybe to a 1-dimensional or 2-dimensional solution space. Okay, and this brings us to a second quite important part. So if we now proceed with the thing, for every constraint, we have to build our linear system, and we have this h and this b term. And if you look now to this hij, so this was the matrix that was generated from a single constraint between I and j. This was this big matrix with these 4 blocks. And the question is, what is actually the rank of this constraint if we have our 2D post constraint? So this was the first example. We measure delta x and delta y. So what's the rank of this matrix? For that, you need to know how the matrix is constructed. So these hij was given by Jacobian transposed ij, information matrix Jacobian ij. So this guy may have full rank 3 in this case, because it's a 3x3 matrix. What about the Jacobians? Oh, sorry, this is yeah. What is the dimensionality of the Jacobians?
Is this 2?
Yeah, close. What is it? It has 2 dimensions.
Because landmark only has x and y, and the last parameter is just a scalar of y.
So it's a 2x3 matrix, the Jacobian. Exactly. So because so we have a 2x3, and if you have a 2x3, these are 2x3 matrices, and the matrix built up by the matrix transposed, so J transposed J. So the hij cannot have more than rank 2. And so this results from the fact that the rank of A transposed A is the same than A transposed is the same than A. So it has the rank of the Jacobian. The Jacobian is a 2x3 matrix, so it can have at maximum rank 2. Okay, so we only have, maximum we have a rank 2. How that differently from for the bearing only case, what is the rank of the Jacobian there? Or not the rank, what is the dimensionality of the Jacobian for the bearing only case?
1 times 3.
Exactly, it's a 1 by 3 matrix. So if you have 1 by 3 matrix transpose times a 1 by 3 matrix, what's the maximum rank that this matrix can have?
1.
Exactly, it's 1. So in case of the bearing only case, we have that Aij has maximum rank 1. Okay. Well, these are two important things. So here, kind of with one observation, kind of one dimension maximum and 2 dimensions over there. In order to generate a constraint between 2 poses with x, y, theta, we need to have 3, right? Because the transformation has 3 parameters. Okay, this gives us to the point. Consider we have a robot that observes a 2D landmark with the delta x, delta y sensor. That's the position of the landmark. The robot observes it. Where can it be? So if I have a robot which observed this landmark, so I know the pose of this landmark perfectly, and so I get a delta x and delta y, where can the robot sit? In this, exactly, it sits on a circle around that landmark. So the robot can be somewhere on that circle. And depending where it sits and depending where it looks, it can everywhere on this circle, I can generate one point on that circle with one specific heading where it generates exactly this delta x and delta y measurement. What does it tell me about the solution space? So what's the dimensionality of this solution space? How many parameters do you need to describe this? A point in a circle. How many parameters do you need to describe where the point lies on a circle?
1.
Yeah, 1, exactly. So this is a 1D solution space. So, for example, parameterized with an orientation from some point. Then you know where the guy sits. Okay, so the pose of the robot is 3-dimensional, x, y, theta. We have a constraint which has rank 2. That means what remains is a 1D solution space. So this is the result. So if we have only one observation, we can't identify a unique solution where the robot sits. Right? So we know where the position of the landmark, we know what the robot observes for that landmark. If we don't have any further information, in this case we have a 1D solution. So we need more observations that the robot travels or of a second landmark, and then we can identify where the robot actually is. So consider the robot also observes the second landmark which sits over here. I actually get 2 circles over there, right? And then I can intersect those circles, and I can actually typically then check how the orientation match, and I can identify where the robot is. But I can't do that with a single observation. Okay, so this is a 1D solution space. What about the bearing-only case? Oh, damn. Okay, okay, it's gone. So the robot, the thing is, if you have only measured the orientation to a landmark, that means that you can be anywhere in the xy along the xy plane as long as the orientation of the robot is relative to is constrained. The heading is constrained with respect to the robot's pose in the landmark. Because you see, let's say, 90 degrees to the right. See the camera 90 degrees to the right. I can move along this line. It will always perfectly see the camera at 90 degrees. And I can actually also move around. So I can reach any point in the xy space. The only thing which is constrained is the orientation of the platform. So if I have a camera, I just observe a single feature, I know the orientation of myself with respect to that landmark. It can be still anywhere in the xy space, but for every point in space, my orientation is fixed. So we have a 2D solution space. Of course, we can find every point in the xy plane, but then we can't fix then the orientation is given. So we have a two-dimensional solution space which is constrained by the robot's orientation. Okay. So in all these examples that we have seen here, where we observe, or where the rank, where we don't have a full rank of our Hij, we have the problem that the system can be underdetermined. That means we may not have collected enough observations in order to find a unique solution to our problem. Maybe we don't have a unique solution, we have a solution space, and how many dimensional solution space where we can be. If we collect enough information, we observe features from different positions, and we have enough observations between all poses and all landmarks, then it's fine, we can solve that. But if we just miss that for one single landmark, we just see it only once and we don't know exactly where it is, then we end up having a solution space, which is difficult because we need to have full rank, matrix H in the end, in order to find a unique solution for our overall optimization problem. And this can lead to the case that our solver in the Gauss-Newton approach simply says, sorry, I can't simply compute a unique solution. Determinant of your matrix A is 0. This is the problem we had also when we didn't add the reference to the global the constraint for the global reference frame in the beginning. We will end up having the same problem. Simply can't solve that system with a unique solution. So we need to make sure we have enough observations in order to actually find a solution. So we had that before, actually mentioned that already before. How many 2D observations do we need to resolve a single robot's pose? So we have a single pose of a robot, and how many landmarks do we need to see to know where the robot is if you have a delta x, delta y observation?
3.
Why 3?
Because those circles have if you have two solutions, because the intersection of two circles are 2, and then last third one find it.
But consider that you have the orientation is constrained to be on that circle. So typically 2 are fine. I mean, there are some maybe an impulse configuration, but typically for example, if the landmarks are exactly at the same position, then it doesn't work. But typically 2 are sufficient because you kind of have a rank 2 constraint. You need to identify. You have a 3-dimensional 3 dimensions of your for the robot's pose. So 2 are typically sufficient. What about in the bearing only case? Exactly. We typically need 3 observations or 3 landmarks we need to observe, where we know where the landmarks are in order to identify where the robot actually is with respect to that. Okay, so in practice, if we implement that, we can't actually guarantee that we, for example, see every landmark sufficiently often. So there's no guarantee. And the problem is if we don't have that, we run into problems. And other things you may imagine, if you have a robot which doesn't have any odometry information, then you also miss the links between the poses of the robot, and you need to observe from every pose a substantial number of landmarks that you also see from the next position, or to relate the poses with each other, and then the problem even gets even worse. And the problem is the Gauss-Newton approach will actually fail to compute a solution for you if you run into those problems. So one of the things you can do, this is the so-called Levenberg Marquardt solution, or leads to the Levenberg Marquardt algorithm. Instead of solving h delta x equals minus b, I solve a slightly different system. And this is this. So I replace a matrix H by H plus a term lambda, a scalar lambda times the identity matrix. What is the effect of this operation? So I have a matrix H, and I add the identity matrix times a, say, potentially very small scaling factor.
Is it like adding noise?
No, you're not adding noise. If you look to the rank of the resulting matrix of this system that you solve.
We increase the rank.
So we may increase the rank of the system. There are situations where you may screw up something for special lambda parameters, but what this typically means, you generate a system which has full rank. So the smaller our parameter lambda is, the closer I'm actually to the Gauss-Newton approach. And kind of like what I can do is I can start with a really small value and just increase the value until I can actually solve that system. So this is a damping factor, and the goal of this damping factor is to make the system positive definite. And what it actually is, if you do this combination, what you do when solving the system is actually a weighted sum between Gauss-Newton, which is h delta x minus b, and a steepest descent approach. Because you have the identity matrix, here you have the delta x, and you have the b, and in the b, consider what the b is, sits the Jacobian. It's the first derivative. So it's actually a form of steepest descent that you execute. So what you do if you use this system, so intuitively first you say, okay, I integrate this damping factor that makes sure that my system is positive definite. But what you are in practice doing is actually making a weighted sum between a Gauss-Newton and a steepest descent. So you can see that as if you're actually pretty close to the solution that you have in practice, you're quite likely to be dominated by the Gauss-Newton solution. If you're far away, sometimes the steepest descent has a better impact on that. So what you need to decide is actually how do I actually set this lambda? And so what should that be? And the Levenberg Marquardt algorithm, so there's a simplified version of that, simply adjusts this parameter over time during the search. So you have your initial guess, and while the system is not converged, you start with one initialization parameter of lambda. So you set that. And then you build your linear system. You compute the error of your linear, so the current error configuration of your graph, of the current graph configuration. You make a backup of your old pose, and then you solve this system over here with your initial parameter lambda. And then you update the pose given the solution. So you add the delta x, and then you check how did the error change. So the error of this new configuration, is the error bigger than the one of the old configuration? If the error is bigger, I might have screwed up something. Maybe my lambda factor was too huge or something else went wrong. So say, okay, I just kind of I do a restore operation, go back to the previous solution and increase my lambda by a constant factor, let's say 2. So I increase the lambda. So I'm more towards a gradient descent operation that I want to do. Or if this is not the case, if the error decreases, I say, okay, let's try to make my lambda a little bit smaller. Because if I'm a little bit smaller, I'm more towards, or quite likely more towards my solution and end up in a configuration that I can solve with Gauss-Newton. But if it's too small, again, I will screw up, and then you have your system, then you're in this situation again, then you increase it again until the system converged. So the simplified version, there are different strategies how to set those parameters, but this is kind of one of the standard techniques that are used to solve those systems, or one of the standard solutions. Actually, something which you may have heard already, this is the problem of bundle adjustment. This is a special instance of what I've talked here. And what bundle adjustment typically refers to is that your sensor is a camera, and you observe only heading information to landmarks, and you want to do a full 3D reconstruction of the scene. So it's not only in 2D, typically refers to 3D. And so what you want to do, you want to estimate the position of the cameras at every point in time, and you want to estimate the location, x, y, that location of the features in the space, and you do it exactly in the way that we have done that here. So you use the Levenberg Marquardt algorithm, or it's one of the, let's say, standard solvers for these bundle adjustment problems. And what is typically minimized is the so-called reprojection error. That means, where do I expect to see my feature, in which pixel on my camera image, and where do I observe it? And I take the Euclidean distance between the pixel where I see my feature, where I expect to see it, and I want to minimize this error. It's what's called the reprojection error. So if you you reproject where you think the landmark should be in your image, how well does this match with the real observation? And this is a special instance of this problem, which is, has been actually developed in photogrammetry in the 1950s. So actually quite a while ago, when we were not probably thinking about robotics or about the SLAM problem in robotics. It was definitely earlier. And also it's very frequently used in computer vision for also doing reconstruction. So these are actually very, very, very similar problems. In robotics, we sometimes can exploit whatever some additional information. So we may have odometry, but computer vision people often do not consider to have. They just take images or a collection of images, or they may, so we can exploit that. Or the thing is that we typically use the same camera to do that because it's one camera which is mounted on the robot. If you do that in the computer vision context, you may want to do that from whatever consumer cameras. A lot of people uploading images on Flickr, and you actually want to do a 3D reconstruction, so you need to estimate the camera parameters for every camera separately. So there are certain things or certain aspects of the problem that can be different if you looked into the individual fields, or they make different assumptions. But the overall problem which is addressed is here very, very similar between what happens or what happened in photogrammetry, what happens in computer vision, and here in robotics. So there's actually a very, very close link between those fields. Okay, so what I was talking about here today is graph-based SLAM for landmarks. I talked about a kind of slightly simplified version here where everything is in 2D. We only have one orientational component, which makes things a little bit different. If you go to the three-dimensional space, or X, Y, Z with three angles you arpage roll, you may run into some things maybe a little bit more tricky to implement here. But in the end, it boils down to more or less what I present here, building on top what we have learned in the, since the beginning of the year for least square SLAM. The rank of this H matrix matters, so you need to make sure the closer you are to a positive definite matrix H, the easier you can actually solve your system. And the Levenberg Marquardt approach was one way to actually solve that problem if you don't have full rank of H, by adding this damping factor times the identity matrix, and this gives you a weighted sum between a steepest gradient and a Gauss-Newton approach. So there's also very special instances on how to solve this problem and how to address landmark-based SLAM. And just one work which I would like to mention. This is an overview which actually is also a couple of years old now, but which gives an overview about this, or an overview about the different bundle adjustment methods, which also have been used in photogrammetry years ago and which are used in computer vision in order to do this full 3D reconstruction based on image data. Okay, that's it from my side for the first hour, and we are going to